Okay, first part, prediction with expert advice. Second part, I will speak about perceptron algorithm, the kernel technique for perceptron algorithms. So second homework question is related to this. Well, actually, I gave the homework question in the previous seminar, but I postponed the deadline because we were a bit slow with the theory. So we generalize the online mystic model in the agnostic setting. So again, think about our example. So 20 years ago or something, I organized activities for children, and I need to tell them 3 days in advance what was the activity. And if it was, I had to decide whether it was indoor or outdoor activity, because the children so it was very difficult to control them inside. But when it rained, being outside, they absolutely didn't like. So I looked to several weather websites. Well, 20 years ago, there were no websites or no interesting one, but imagine that they existed. Also, I should focus on the essence. So imagine you look to weather websites and they give possibly contradicting information. There are even days where all websites are wrong. And then you make a prediction. You suffer some loss. Then the next time you look to the website, you get new predictions and you suffer some loss. And the goal of the model is to aggregate the predictions and a good prediction. And your predictions, the number of mistakes, should be as close as possible to the number of mistakes of the best websites, or even better, of course. But to make a bound, we try to get as close as possible to the best website. Okay. So now, in the seminar, there was an exercise that how close can we get to the best website? It was a factor 2. We cannot go better than a factor 2. And what was the problem a bit there? You can have days that the websites differ in opinion, but you have to say an answer, rain or sunny. And so we will extend the model and allow to tell you like, okay, I don't know. I will say something in between. And when you do this, you get a certain small loss. So in the example with children, you can say, okay, let's think very hard for an activity that works both inside and outside. So then you're fine in both cases, but you need to come up with a great idea. You need to invent a great game. And so it's harder the more constraints you have. Yes, so here is the game. There are 2 players. They're called forecaster and environment. And the forecaster, it receives a set of predictions from experts. Then it needs to make a prediction, and then it receives a true label. This happens in each round, so then it's iterated. And so we will assume that the predictions should be real numbers, and the labels are also real numbers. So here is a game more formally. So we have a set of predictions, y. So for example, -1 plus 1, or it can be an interval from -1 till +1. Then we have a set d of predictions we're allowed to make. And so d can now be bigger than y. Then environment. Okay, so we receive the experts tell us their predictions from the set y. Then we make a forecast in the bigger set d, and then we get the outcome y, which is again in the set y. And for loss, we will use the difference of absolute values. I will just to make things concrete, I will fix 1 loss. Okay, 1 student disappeared. Maybe there is something wrong with the sound. So please write in the chat if something is bad. But yeah, you cannot hear this. Okay. Yes. So we will also look to the loss of the experts. So instantaneous loss is this PIT, their prediction minus the true value, and then take absolute value, and the cumulative loss. So cumulative loss is LIT denoted. So the total loss up to around T. And we want to keep the regret small. And the regret is loss of forecaster's prediction. So the cumulative loss of forecaster's prediction minus the loss of the best expert. So RT we want to keep small. And in the previous lecture, we have seen that RT is at least, so imagine that Y is equal to -1 plus 1. So the set 2 element set -1 plus 1. Then in the previous lecture, and D is equal to Y, then the loss, the regret is at least T. So even if we have only 2 experts, so what are the parameters of the game? There is the set Y, the set D, which are subsets of R, the number of experts, and the number T of rounds. So 4 parameters, yes? So this is agnostic setting. It even generalizes. Before we had a set of classifiers H, and so we used the classifiers as predictors. And now predictors can be anything, so they can be inconsistent. So the expert can now, for the same input, well, there is actually no input. So just can be anything. Yeah, so it's agnostic setting. So environment can choose its YT however he wants. So 2 players, forecaster and environment. And so we can, so previous lecture, we say that there is a way. So imagine that Y is equal to -1 plus 1. Oh, sorry, let us say Y is 0 or 1 and D is 0 or 1. And then last lecture, we said that we can have loss, regret T over 2. And the idea is that even if n equals 2, only 2 experts. And what should environment do to enforce regret at least T over 2? So environment will choose first expert, for example, always equal to 0, the second expert always equal to 1. So P1T always equal to 0, P2T always equal to 1. Then forecaster says something. Then environment chooses the outcome, always the opposite of what forecaster sent. And then we can look to the 2 losses for this particular strategy of environment. So forecaster will have maximal loss, and around T, it will have loss T. And the experts, they each time send the opposite. So the sum of their losses will be exactly equal to T. So that means one of the 2 experts will make at most T over 2 mistakes. And so in every round, precisely one of them is wrong. So one of them has loss at most T over 2. And then we look to the regret. So in the last line, L hat T is equal to T, and the minimum is at most T over 2. So we see that the regret is at least T over 2. That was in the previous seminar. And now let us take a bigger action space. It's a bit unfortunate. Okay. Let us now take a bigger action space. Let us take 0, 1/2, and 1. That's the next slide. And then I claim that there is a strategy in which predictor has loss at most T over 4. So that's the last line on the slide. Forecaster, sorry, has loss at most T over 4. So how does it work? What is his strategy? he will predict, so the strategy is called follow the leader. So he will always listen to the expert with the smallest loss. If both experts have the same loss and they make a different prediction, then he will use his 1/2, his move 1/2. So he's so D is equal to 0, 1/2, and 1. Or here I said D equal to the full interval. So it doesn't matter. He just uses 0, 1/2, and 1. And so I repeat, his strategy is just to follow the best predictor unless both predictors are equal, have the same loss, and they make opposite predictions. Then he will say 1/2. And so can you see why this prediction strategy has regret T over 4? So at least if T is even. So here we will look at pairs of rounds for this. So silent. So we follow the leader. So let us look in the top line. You see the definition of regret. So what happens in a round where there is a leader and he is wrong? So imagine that the losses are different. So at any moment, the two experts, their loss is integer number, right? Because the experts can only predict from the set Y. So I remind you the previous set. So the experts must give prediction in the set Y, but we can use more values. That's how we try to bound this linear regret lower bound. That's how we beat it. And so we previously we had in round T, we could have regret at least T. We had the lower bound. We're gonna beat it. We will have, we had T over 2 lower bound. Now we're gonna have at most T over 4, and we beat it by using extra values in the prediction. Okay, so our experts have to say a set and have to say 0 or 1. So their loss goes by integers. Let us look at the round where they have different losses. Then we listen to the expert with the smallest loss. So what happens with the regret if he is wrong? Well, if he is correct, then the losses don't increase and we are happy. But if he is wrong, then yeah. Also 1 point. So the best expert's loss is increased by 1 point. Yeah. Okay. So we consider the same example again with 2 experts. I forgot to tell this. So we have 2 experts. They say something different. That means so we assume that their losses differ by at least 1. So the loss of the best expert goes up by 1. That means the minimum goes up by 1. Because the other expert has at least 1 bigger loss. So if the smallest goes up, the minimum goes up. Okay. So in rounds where the losses are different, we see that the regret cannot increase. So the only place where the regret can increase is in rounds where the losses are equal of both experts. Okay, so can you now finish the proof? Yeah, exactly. So well, if both in a round where the losses are equal and both experts agree, we give the same prediction. And so the regrets remains the same. either everyone is correct or everyone is incorrect. But then if the expert give different predictions, then we use 1/2. So our loss increases by 1/2. But since the expert give different predictions, one of them's loss increases. So in the next round, the losses of the experts are different. And so we are again in the case where we have a 0 increase of regret. So in the worst case, in 2 rounds, our regret increases by 1/2. So after t rounds, we have at most t over 2 increases by 1/2. So we get a regret t over 4. And it turns out we can do even much better. So if the if the set D, sometimes called action space, is a continuous interval 0, 1, we can have something with square root that grows by square root t, or a small number of experts. Okay, sorry, you are asking me something. Yeah. Previous. Of what? Of LYT is the cumulative loss of the ith expert at time t and round t. Okay. So now let us go. And the algorithm is called, so previously we spoke about weighted majority algorithm. Now it's called randomized weighted majority algorithm. Okay, and I will switch to labels -1 and +1 since it's closely related to majority algorithm, weighted majority algorithm. So that's the bound we achieve, square root t times natural logarithm of n. So log is binary logarithm, ln is natural logarithm. So if you use Mori's book, note that log denotes natural logarithm. Okay, we will use a constant alpha, which is, well, there's a mistake on the slide. Alpha is bigger than 0 and bounded by a 1/2. And I will use Lmin for the loss of the best expert. And the plan is to prove, to give a strategy and and prove the bound on the loss of the strategy by 1 over alpha, the ln of n, number of experts, plus 1 plus alpha times L of loss of the best expert. Okay, there are more mistakes in the slide. I'm sorry for not updating. Okay, let's show the lecture notes. Or I can use my pen and make some annotations. White color. So here we need 1/2. First, let us look at this bound. So we are interested in, so let us assume that we have proven, we have proven this thing. So we have proven this thing. So then we are interested in the regret, which is the loss, the total cumulative loss of our algorithm minus Lmin. So this term disappears, and we want to have a good bound. So let us take the optimal alpha. And the optimal alpha, if you compute the derivative, you will see that it's equal to ln n divided by Lmin. Now there is a problem. In the game, Lmin is the loss of the best expert. It's not fixed in advance. So we cannot use this value of alpha to fix our strategy. So the strategy will depend on alpha. It's a parameter we have to set in the beginning. So recall the weighted majority algorithm. It also has a parameter. We called it beta, I think. I don't remember. So this is the same thing. To update our weights, we will use almost the same update algorithm for the weights. but we need to fix it in advance. And so in the beginning, we don't know L-min yet. So we will instead use an upper bound of L-min. We know that the minimum loss, since predictions are, oh, what did I say? I don't know what happened to the slides. D is the interval between 0 and 1, and y is -1 plus 1. Y equals 0, sorry, y equals 0 and 1, just like in the previous example. So in this case, we know that L-min at time t is bounded by t, and we will use this upper bound in our choice of alpha. So this doesn't work, and we set alpha equal to ln n divided by t. And for this choice, unfortunately, alpha needs, okay, if we assume that alpha is indeed smaller than 1/2, bounded at most 1/2, then we can apply this bound and we are good, because this bound becomes, I will write it here, square root t over ln n times ln n plus, so we subtract L-min, so we don't need to deal with this. We can just look at this, plus square root ln n divided by t times L-min. Since square root t is bigger than square root L-min, this thing will be, so we divide by something bigger, so this will be at most 2 times precisely what we need here. So after we've proven this, we are good, assuming that this relation holds. But if this relation does not hold, if the number of rounds is too small, we are also good. And this follows from this relation. So if we multiply this by ln, sorry, if, so the regret is also bounded by t. Yes? So at any moment we have regret at most t. And under this assumption that this is at least, so imagine that ln n is bigger than, so 4 times, so let's write it in this way. If we assume that t is smaller than 4 times ln n, then we have that t is smaller than, okay, let us multiply this by t, we get t squared, and then take the square root, so this is nothing, we take the square root, then we have 2 times square root t ln n. So that's precisely what we need. So then we are also happy. So in both cases, for big T and small t, we achieve this bound after we can prove this. Yes. Okay, so that's our task now. And now it's time to present the algorithm. So are there questions about this part? People seem more or less awake. So even though it's Friday. Okay, some people are still thinking, some stop thinking. So let's clear all drawings and go to the next slide where we prove our goal. Okay, so here I will present the algorithm and then I will remind you about the goal. But the algorithm basically we already know. So for the prediction, before we took my weighted majority algorithm, right? Because we had to choose one of the two labels. Now we can choose something between 0 and 1. So we have extra power. And for this, we don't need to compute the majority and just look at the weighted majority. So again, we will initialize weights and we will decrease them by constant factor each time an expert is wrong. And now we have a very interesting relation. So our prediction, so the instantaneous loss that we receive is y hat t minus yt. That's by definition of the game. And this is precisely equal to the normalized weight of all experts that were wrong. So if every expert is wrong, this will be equal to 1. And we will be maximally wrong. But if they're all right, then we will incur 0 loss. We lose 0. So do you see why this is true? So a few people see it. So just think about the two cases. Imagine that that the true label is 0. Then the loss we incur is just given by okay. So what is y hat? Y hat is the weight of all experts that say 1. Yes. So y hat we can say, oh, is weight of all experts I that say 1. PIT equals 1. That's YT. Y hat t. So if YT is 0, then this is just equal to y hat t. It is normalized weight. Well, I say weight, normalized weight, because we have a denominator here. So then YT is equal to this, and that's just the normalized weights of all predictors that say 1. So not equal to 0. And if this is 1, we have something symmetric. Then this is the normalized weight of all predictors that say 0. Okay, so now we need to remember, try to remember this relation. So this we don't need to remember, that's a part of the proof, this equality. So normalized weight of all predictors that are wrong is equal to our loss. So let us clear all drawings. And yes. Yeah. Okay. But this will not happen because we assumed alpha smaller than 1/2, between 0 and 1/2. So the question is, can weights be negative, and would it be better to use negative weights? So imagine that a predictor always says the opposite. Then we would be very happy and start to believe him. And so the algorithm doesn't think about this. But you can, it's a very good idea to improve it in this way. That's, yeah, it's a, well, but you don't use, so in this case, it's better to have 2 experts. I think it's better. I don't know how to. So there are questions. There are 2 different questions. So if we want to think about very bad experts, then one approach is to have to double the number of experts. And for each experts, add one that always says the opposite. And then we can also run the algorithm. However, if you want to change the update rule, so that for very bad experts, their weight becomes negative. I don't know how to do this and then give a proof. So I should think about this. And if yes? No, I can increase the set of experts to 2n and then run this algorithm with increased set of experts. I think it's a good approach. So if you expect that you have bad experts, however, the approach that you suggested is like, how can we use negative, let's assign negative weights to bad experts. They're well, you need a new update rule because 1 minus alpha, it's number bigger than this number bigger than 0, this factor. So we start with positive weights, and then after each update, they remain positive. So there are no negative weights. Yeah. Yeah. So if you want, one needs to think how to change the update rule at negative weights. Okay. Let's remove, clear all drawings. So now the algorithm is clear. So we take normalized weight, or predictions normalized weight of experts, and each wrong expert, we decrease his weight by factor 1 minus alpha. So before we had just a factor beta, but then it turns out computations are much easy if you change the name of the constant to 1 minus something. Okay, that's what we wanted to prove here. And we will use the same strategy. We will again say that here is the weight of the best expert is bounded by the sum of all weights, and in each round, the sum of weights decreases exponentially according to the laws of our algorithm. That's all algorithms we've seen before use the same technique. And now that's our plan to again apply it. So what we have to do is to look to how fast the sum of all weights decreases. And this happens in our first part here. So let us look to one round and see how the sum of weights decreases. So all the, okay, so LT, so what we do, all bets, all experts that made bad predictions, their weight that get decreased by 1 minus alpha factor. And we know that this is equal to the normalized weight of bad experts. Wait, my pen is not working, but you remember it. Normalized, this is the normalized weight of all bad experts. So if this is LT, we multiply this weight by 1 minus alpha. And the other experts, they have the same weight, which is 1 minus LT. And now we need to compute something. So what we can do is this LT cancels with this 1. And what remains is 1 minus alpha LT. And now we use this rule, 1 plus u is bounded by exponent of u. This holds both for positive and negative real numbers u. And so this explains this last inequality. And now we manage to upper bound the decrease of the weights by something smaller than 1, but something bounded by 1. So if we make a lot of loss, this factor will be small. And now we apply our plan. So the sum of these weights is bounded by the sum of initial weights, Wi1, times all these exponential factors. Exponent minus alpha, the loss at time 1. So our loss at 1, exponent minus alpha, the loss at 2, and so on. Loss at time t. So the little l is our instantaneous loss. So when we work out this exponent, we have precisely this, our exponent minus alpha times the cumulative loss. And recall that the initial weights were all equal to 1. So when we sum overall experts, we have n the number of experts. Okay. And so we've proven this inequality. And now we just take negative logarithms. So then we have ln n appear, oh no, positive logarithm. We have ln n that appears here. And then I take the logarithm of this and I put it on the other side. So we have an additional minus sign here, and it's on the other side. And this also appears with a minus sign, so I put it on this side, and so we get this thing. And so we have proven this thing. And now we need to just use some strange inequality. This inequality holds for all alpha at least 0 and at most 1/2. So that's why we had to assume alpha is bounded by 1/2. And so if alpha is small, then we can use Taylor approximation. So you need to prove this. If you want to prove this rigorously, then you can see that it's true for alpha equals 0 and compute the first derivative. First derivative of this will be some polynomial. And then if you multiply everything, you will see all cancels. So the first derivative of both sides satisfy the same inequality, provided alpha is between 0 and 1/2. So it will be some quadratic polynomial with the solution 0 and 1/2. Okay, so but this silly computation. So how am I doing with time? Not so good. Let's erase everything. Clear all drawings and go to the next thing. So let us go to the theorem. So note that here we used d equal to 0, 1 and y equal to 0, 1. And then we prove this inequality. Now we will improve it. We will improve it for y equal to 0, 1. So now the expert can have a broader range of predictions. So our task becomes harder. Environment has more moves he can make. And we will prove this with the better coefficients. So we will obtain 1/2 t times ln n. So we will both improve the bound and the strength of the game. But unfortunately for this, we need to use like heavy mathematical words like Jensen inequality and Hoofding inequality, and probably you already know them. So, but let's review them because I never know who comes to my courses, and there are problems. It's pleasant to review these inequalities. They make me always happy. Maybe you too. Clear all drawings. So let's go to the two intermediates, Jensen inequality. And so there is a cool question. And so imagine you wonder whether you're fat or not. And so is it possible that you have average length? So humans, when they grow, of course, they're more heavy, right? Bigger. If a person of 1 meter 20 weighs 120 kilograms, maybe it's a big problem. But if a person of 2 meter 20 weighs 120 kilograms, probably it's fine. So then is it possible that you have average human weight and average human length, and you're still way too heavy? So can this happen? Yes. Yeah, of course it can. Yeah. well, there is BME indexes and so on. Okay, I will change the question because for human it's very noisy and wide bounds for BME and so on. But then for fish, there's very clear relationships. So there is shark, a special type of shark that is very happy when they're captured, they're calm and you can measure them. And so everyone studies this particular friendly shark type. I don't know. I think they still eat humans, but when you capture them, they are very calm and you can measure them. And um, and so they measured in a big population. They measured all the shark. Every point is a shark. Well, I guess male and female. And there is even a third type. So there's also non-binary genders for these sharks. I don't know. Yeah. So and this is a relationship, and you see that they have like almost cubic. So there are no error bounds here, but this cube, and it's logical that length versus weight is cubic relationship because sharks grow in 3 dimensions. I mean, the water is very easy for supporting weight, and so no special muscles are needed. Okay. And so let us, I've taken this graph and then computed average weight and average length. And then you see that if a shark is here, then he is 50% overweight compared to sharks of the same length. So you could say that this one should take a diet if it exists. Okay. And so why does it happen? And it's because some phenomena are studied by Jensen Inequality. So since the weight goes up by 3rd power, the heavy sharks get a huge influence on the average weight. But relatively, they have smaller influence on the length. So that's why this point is pushed upward. Okay. Why this point goes up. Okay, and that's Jensen inequality. So if a function is linear, then average of function values equals function value of the average. But if the function is convex, then the values are larger than the trend in a point, than this line that goes at a point, and so average of values can only be larger than average value of average. So that's, and so you can say it in mathematical detail. So a function is convex. If you look at convex combination of 2 points, and if value of convex combination is at most convex combinations of values. And then there is a lemma, f is convex if and only if this relation holds. And it's simple lemma. There are some very subtle analytical points, but we don't care about them. And then if you take expected value of this relation and set x tilde equal to the expected value, you immediately get this relation. So we set x tilde equal to this thing, and then you take the expected value of the relation here, then this drops, and you have proven Jensen inequality. And that's for functions that map real numbers to real numbers. But you can have here any vector space. So you can take any input that's a vector space over the real numbers. And so you can do the same thing. So you need vector space over real numbers because you have here these coefficients and you need to add them. Okay, now people get sleepy because you know already all this. So let's go to the next one. Yeah. So there is cool application of Jensen inequality. It's called arithmetic geometric means inequality. So have you learned how you get it from Jensen inequality? So if you haven't learned it, you can read it in the lecture notes. You just have to take the logarithm of this inequality and take uniform distribution. You first prove AMGM and then use it for Jensen inequality. Okay, yeah. AMGM is like in many, they when you learn to optimize something in multiple dimensions, it's standard exercise, but it's much nicer to prove it with Jensen inequality. So I would never use this exercise if I teach optimization. Okay, but that's philosophical. I should not be distracted and continue with the lecture. Okay, now second intermezzo, which is even shorter. So here we have Jensen inequality. That means that this inequality holds because exponent is convex function. Second derivative of exponent is positive because it's exponent itself. But very often you will need other inequality. You will need something like this, and we already know it's not true. So we will need to increase this somehow. And that's what Hovding lemma does. So when we take expected value of some random of the exponent of a random variable, then we can bound it by exponent of expected value plus something small. If eta is equal to 1, then just we have to add 1/8, which is something small. So you've already seen this too, this lemma of things. Yes, a few people. Yeah, it's used. Yeah. There is Hovding inequality, and there's a generalized version of Chernoff bound. Chernoff bound we will use all the time in the next 5 lectures or something. Well, we use something more general, but okay. Let's not go too fast. Let's start with Hovding lemma. But tomorrow in the seminar, you will need it for exercise about nearest neighbor algorithm. Sorry, clear all drawings. Okay, so here we assume that x is in some interval of size 1. So usually a is equal to 0, but I will state it more generally because it will help us with the proof. Okay, and I will, so note before I said that here is 1/8. But the proof with 1/8, it's very long computation. It's boring. I will not ask you and not tell you. We will just do a little bit weaker so you understand that this is very logical, that this is easy inequality. It's not so surprising. Yes? Yeah, it's most optimal. So I do. Yeah. If you do 1/9, then it's counterexample. There exist counterexamples. I mean, for some case you might be lucky, but I think for if x is just binomial variable 0, 1, it's already false. Yeah, because if that would be better, yeah, then no, then everyone would talk about this and we would use better Chernoff bound. Okay, so it must be false even for binomial variable. Okay. Sorry, I mean Bernoulli variable. That's okay. So let's go to the proof. So here we can assume expected value of x is 0, and the reason is that if we replace x by x plus some constant c, then in the theorem, in the statement, we just have to add c here in both bounds and nothing changes. Right? So we can just subtract expected value of x here. And if we have the special case proven, then we can again, add back expected value of x. So we prove this special case. So, and then I note that if eta is bigger than 1, so if expected value is 0, then we know that with probability 1, x will be between -1 and +1. Or even that's enough. X is bounded by 1. And if x is bounded by 1 and eta is at least 1, then this is trivial. Since this we already dropped. And if eta is bigger than 1, x is bounded by 1, it's easy. So then we can assume eta is small, at most 1, and we can also, and we all also know that x is at most 1. Okay, so now we will use an inequality. So there is 1 plus u squared. Sorry. Let me write it again. X of u is bounded by 1 plus u squared. Come on. Clear all drawings. You know that 1 plus, I will in the same time write the other one that we use. 1 plus u squared. But for this one, we need to assume u is at most 1. If u is very large, of course, exponential will beat any polynomial. But if u is small, this holds. This one always holds. Okay, so let's do the proof. So we start by applying the right inequality, this one here. So here we have eta x plus eta squared x squared. X squared is bounded by 1 because x is bounded by 1. So this inequality is okay. Then we take expected value. So again, some problem with the slides. I take expected value. This one is not Taylor. You can check derivatives. Yeah. So Taylor works for positive u because exponent u is these are the first two terms of the Taylor expansion. But for negative u, it doesn't work because the Taylor has negative terms. But then you can check first derivatives and that is okay. Yes. So after we've proven this inequality, we can take expected values. And what we see is that this one falls out. And so we see that this thing is bounded by 1 plus eta squared. And now we use this one. So actually we are just saying if, so why does this inequality hold? Well, we set expected value equal to x, and we assume that eta times x is small. So this is very well approximated by 1 plus eta x, and then it's quadratic term. And so then we can just move from in, out in the exponent, and we are good. Okay. So it just problem is that people become very scared of Hoeffding lemma and Chernoff bound, Hoeffding bound, and so on. So I say that the hardest step is actually easy if you sacrifice a bit of precision. And if you want to be maximally precise, okay, then you need to suffer for the computation. Okay, I need to speed up and stay focused, clear all drawings. Now we are ready for exponentially weighted average algorithm. Okay, and that's just the algorithm and then one slide for the proof because it's the same thing again. So we take the same prediction. So the YTs are again weighted average of predictions, but now we use exponential function to decrease the weight. So what's different here is that experts can tell some number in 0 and 1. So we cannot decide whether they're right or wrong. They can be a bit right. And we decrease their weight to the extent that they are wrong. And that's, oops, and that's what is said here. Okay, so you should try to remember the last line because that's new. And so we have some parameter eta. Eta should be at least 0. It should be positive. I don't think there are other requirements. No other requirements. Okay, and here is the proof. So on the top is what we aim for, and we apply again the same technique. So we will look at a fixed round. And so here is some notation. Let me explain it. It is, so I will denote this thing here. I will shortly write it, E, expected value of PIT, when I is distributed according to the weights. So I will use this notation here. So we have a weight vector, and then the weighted average I will denote in this way. Okay. So I can even say this. Now let us look what's happening here. So the reduction in the weights is just the weighted average of these factors. So the sum of reductions in the weight. So just we set Wi, it's not difficult. By I plus 1 is equal to exponent of this thing times the weight at WT. So, and that's just by the definition of the symbol. So we divide by the sum of all weights, and then for the ith predictor, we multiply by this weight. Okay, and now we have a nice expected value, so we can apply Hoeffding's lemma. And we can understand the weight as a probability distribution. So here is Hoeffding's lemma. We have the expected value. So here eta is missing. We have the expected value plus our punishment because we applied Jensen inequality in the wrong direction. Okay, so that is the decrease of the sum of weights in one round. Oh, sorry, we're not finished with one round. We want to simplify this expression. We want to relate these losses to the loss of our algorithm. Loss of our algorithm is y hat. Loss of our algorithm is y hat of t minus yt. But note y hat of t is weighted average, so it's written here, weighted average of the predictors. So this is easy inequality. And now we can compare this to this thing. It's the same thing. So we look inside the exponent, we look to this thing. What is it? Here, so we just moved the expected value inside the exponent by Hoeffding's lemma. So what is here is I is proportional to yt. I is proportional to yt. Now we want to move the expected value inside the absolute values. Absolute value is a function that's convex because it is just absolute value. We have r here. That is absolute value function. It's clearly convex. So we apply Jensen inequality. So when we bring expected value inside, we will be below expected value of values. And so we have proven this thing. This is the loss of the ith predictor at time t. So this is precisely what is in the exponent. And so if we make the negative exponent smaller, then our bound only becomes bigger. So this whole thing is bounded by exponent of this vector 1/8 times exponent of y hat minus yt. So that if we combine this and this, and that's what's written here. So here is, so when we multiply by all rounds, so then we have here is a lower bound on the sum of all weights in round t plus 1, capital T plus 1. So that this is the weight of the best predictor. So this is at least this sum, right? Then in round 1, the sum of the weights is 1. And this is bounded, this ratio is bounded by the product of all these ratios over the rounds. The same technique as we've been applying already 6 times. Okay, I need to say it again. So I need to say what's here in between. So this is bounded by sum of weights I at round t plus 1 divided by sum of rounds weights in round 1. Yes, and here we sum over all experts. And in the round 1, all experts have weight 1. So that's n. At around t plus 1, we look to the loss of the best predictor. The best predictor has this loss. So there is one predictor that has 1 times exponent of minus eta, his loss in the first round. So here I multiply all factors. And so the best expert will have weight, will have this weight. So then I bound the numerator by the sum of all weights in round t plus 1. And then I say that this ratio is bounded by the decrease of the sum, the product of all decreases of sums. And we've bounded this product by this thing. So after t rounds, we have this t times. And this here, oh, the eta is missing again, minus eta. So the sum, it will be our cumulative loss. Y hat t is our prediction. Yt is a correct label. So we have eta L here, our cumulative loss, and round t. And so we've proven this thing. And now the only thing we have to do is take logarithms. So when we take logarithms, this comes here. This thing, I can flip sides and take logarithm. It comes here. Then this thing is here. And the ln, again, flip sides is here. So now we only have to divide by eta. And we get the bound that we wanted. Oh, sorry, I forgot to write the bound. So I regret equals to L hat minus L min. And I claim that this is bounded by 1 over eta ln n plus d eta divided by 8. And now there are no restrictions on eta, so we just need to optimize over eta, and we get this thing. Yeah, so we set eta equal to the square root of, yeah, okay. it will be something like ln divided by 1/8 over t. And so we have 2 times the same term, and it will eventually give this factor 1/2. And so now you've seen all of the proof. Yeah, it's in the lectures and the lecture notes. Yeah, it's the hardest proof for online prediction. It's the end of the lecture. I will just, yeah. Yeah, no, I gave a lot of explanations and you will just read it and understand it. Yeah. Yeah, I made slides some time ago, and then I thought better when I made the lecture notes. Okay, so I will quickly say that there is a lower bound. So the upper bound we had was square root. So recall ln n 1/2. And now when we set n equal to 2, we can get this lower bound. But here I changed to y minus 1, 1. So you need to scale also the regret by the same factor 2. So if you want to do honest comparison, then you should have an additional factor 2. And so it's pretty close. Lower bound and upper bound are pretty close, but they're still like almost a factor 2 different. But yeah, note that the lower bound only uses y minus 1 and plus 1. So I don't know what is the status, what assumption is blamed for this missing factor 2 between upper and lower bound. Okay. So the proof I will skip. It's extremely beautiful proof. It touches many nice things, and there is it uses this inequality. I forgot his name. Wally's inequality for pi. You can see it here. It is Wallace equality, and there is 1 blue 3 brown YouTube guy who invented completely new proof. It's amazing that he doesn't care about inventing mathematics. He just cared about reusing his slides for another movie. But in this way, he invented something very amazing. Okay. Now I think we should check the time. So there is 7 minutes left, and I can speak about kernel net. It's important for your homework exercise, for the homework that was postponed. So let us go to lecture 2. So yes, I will maybe a bit late, but not much because it's not so complicated. It's rather short. Okay, so this we've already, so here is Frank Rosenblatt, inventor of Perceptron Algorithm. So Perceptron Algorithm, we used it to learn half spaces. So if your classification problem can be solved by half space, you're very happy, but it almost never happens. It's very rare. So let us look to a very simple example in 1 dimension. So this, if you use half spaces, you will not get good result in this example. What can you do is feature augmentation. So that means that you multiply several features and take powers of them to get more features. So here, this feature, you go from 1 dimension to 2 dimension by looking to the value and it's squared. And so then the problem looks like this. And now you can fit half space and separate red and blue. So that's a very easy idea. And you can combine it with Perceptron algorithm. So it works very well if you have small number of dimensions. So you can do it in 2 dimensions as well. So feature augmentation. So then you go from, for example, 2 dimension 2 to dimension 3. Here I've dropped the linear terms. Yes? No, then, yeah. No algorithm can work in realizable setting. You need to use agnostic setting. But now we speak about realizable setting for the moment. So that's, but yeah. But of course, in agnostic setting, it can also happen after augmentation. You have better classification rules. Okay. And so you can do it, but usually you have like 10,000 features or whatever, 100, it's much bigger number. And if you go to quadratic, if you fit polynomials, then the number of possible terms increases. So you can make polynomials of degree. If there are d variables, then you have d squared possible monomials of degree 2. Well, you have x1, x2 is the same as x2, x1. So it's d squared divided by 2. But if d is equal to 10,000, you have 10,000 points, then you can still deal with normal features, but no longer with augmented features, because you will have 100, the vectors will have size 100 million, and you have 10,000 points. And so, okay, maybe you can do it, but it will not fit in your RAM memory. It will be very slow. It's a disaster. But for Perceptron algorithm, it's no problem, because we can change something. You lose, during training, you lose no time. It is almost no loss in performance. Just in prediction time, you lose a little bit. So how does it work? So let us recall Perceptron algorithm. And we see that we can rewrite it so that we depend on the feature vectors only by dot products. That's the main insight. So here I've rewritten, so at any point, this WT will be a sum of, it will be like a sum of x1 minus x5 plus x6 and so on. This is W at some point t, it's just adding up input vectors. So then if we just substitute these here, what do we get? Xt times x1 minus xt times x5 plus and so on. So we just have to add up a bunch of dot products. That's the key insight. We can rewrite Perceptron using dot products and then find a trick to compute dot products extremely fast. So here is algorithm with dot products. So I will do two things. Explain that it only depends on dot products, but that's already clear, I guess. So this formulation is clear, or you want me to explain it again? So WT is the set of times where the prediction was wrong. So each time the prediction is wrong, we add the current time to t. Yeah. So now we apply algorithm not on xt, but with the augmented vectors, phi of xt. That's the first change. And the second change is we don't store WT, but we store the moments where the prediction was wrong. And then this algorithm is precisely the same algorithm. We just compute the sign in a different way. So you see that the learning part is even faster, but prediction part is a bit slower. Okay. Yes. So we only learn something when we're wrong. But now learning goes very fast. We just add the current time to our list of times where we're wrong. And so here we have WT. Okay. So now the second task. Now I want to convince you that for this trick with polynomials, if we do feature augmentation with polynomials, the dot products are very easy to compute. And it's just something algebra, just very small computation. So let's see on the next slide. So here I take a vector and I take all monomials, all monomials of degree at most 2. So there is the constant x1, x2, x1 squared. For convenience, I have this one 2 times and x2 squared. So more general, if we have d dimensions, here we have d squared dimension. So then let us look to the dot product. If you work it out, is exactly equal to this thing. So if we, so you can just 1 plus x1, x2, x1, x1 prime plus x2, x2 prime squared. And so it's the same as this thing. So you should think a vector here and then pointwise multiply everything. Okay. So that means the dot products we can compute very fast. And that means perceptron algorithm we can compute very fast. Even if dimension is 10,000 and we have 10,000 training set size, it's no problem for us. It's just fraction of seconds. Instead that we have to use a separate hard disk to store augmented feature vectors. It's extremely powerful technique. So it's used in many domains of machine learning, this insight. So if you have a machine learning algorithm that only depends on dot products, you can always apply kernel technique. There are also other kernels. I will mention them just in a minute. Okay, so this is for quadratic polynomials. You can do any degree t. There is no difference in cost. Okay, I will skip this animation. Oh, scheiße, this is some theorem. So yeah, that takes 10 minutes. I will skip it for now because you don't need the proof, and I will tell the proof when we study support vector machines. So then I can finish in 5 minutes. It's a decent time. So I will skip this. Well, I will just tell you, I will not tell the proof, but just what's the idea. So people say, okay, we only need dot products. And we don't use the augmented features. So you can think I have an application, and you can start thinking what would be a good augmented feature vector. But then your feature vector is never used, so it's a waste of work. You only need the dot product. So people start to design dot products right away, since the feature vectors are never computed. And then, but do not screw the algorithm or the mistake bounds. You want a theorem that tells you if your dot product, your kernel function, so they will say, we call it kernel function. It takes 2 objects and it gives you a real number that presents the dot product. So they will design this kernel function. And then they say, we have a theorem that guarantees that somehow these feature vectors exist. And if they exist, it means my algorithms and my mistake bounds will not get screwed. And it turns out there exists very simple theorems. So there exist rules that guarantee that you are most of the time safe. Not always, but a lot of functions are good for kernels. And that's the purpose of this theorem. So given a function k, under which conditions of K does there exist a feature mapping that achieves this? Okay. And so the condition has to do with positive semi-definite matrices. And here is the definition. So I will ask Arthur for the seminar to repeat. Yeah, positive. Oh, you already know this. Yeah. And there is, so we only need one property for them, that they have square roots that are symmetric matrices. So if A is symmetric positive semi-definite, then there is a matrix B, so that B squared equals A, and B is symmetric matrix. Okay. And here is the definition. Here is the theorem. So if we, if for any set of points, okay, so here is criteria with integral, which is very old. It's used long time ago when people had to compute everything by hand. They already discovered this technique. So scientists had special rooms with hundreds of people that were computing things by hand, and they used such techniques. So this 1909, it was invented, and they used a continuous variant. But there is also a discrete variant, and that's in the bottom. So a kernel is PDS, so that's the theorem. So the kernel is good, the feature mapping exists, if and only if for any m points, for any set of points of inputs, you construct kernel matrix here. So matrix Kig in this way for these points. And if this matrix is always positive semi-definite, then the kernel is good. So the mapping exists. So that's the theorem, and we will prove it in a few lectures. Here is a proof for the case where X is a finite set and where we use the square root. Okay, and then for the homework question. So last week there was homework question where you proved for a specific problem, the perceptron algorithm makes an exponential number of mistakes. Well, at least it's your task to prove it. The deadline is tomorrow before the seminar. So check Wikipedia page. I see some panic faces. So there is what's the website? wiki.cs.hsc.ru, and then go to statistical learning theory. And there you have everything from the course, including homework tasks. And but okay, if you didn't know this, send me an email. And if only 3 or something people say I didn't know this, it's no problem. It's first deadline. I understand. So, okay. Yeah. Yeah, but if the seminar is tomorrow, so it's done, then it's tomorrow. There is no lecture, but there is a seminar. Yeah. Okay. I will. I mean this. Tomorrow you have seminar at 6, and you need to submit before the seminar. I think so. Yeah. Last week it was early at noon, and now it's. Okay, I don't know by head when is the seminars, but it should be, yeah. You see it in rules, and it should coincide with what's on the wiki. Yeah, so problem list 1 and problem list 2, only the first problem. And then I put for the second problem that the deadline is in 1st of October, because you're using this stuff. Okay. So now what will we do? When we have PDS kernel, we want to have good mistake bound. And how can we get good mistake bound? Oops. So if we know that So we rely on the existence of feature vectors. And if our inputs, if phi of x, so we have some inputs. Okay, I will skip this slide. I'm afraid there are mistakes. I will directly show the theorem. So what's the plan? We want to, what is your task? You're given a special kernel, and you want to prove that if you use this kernel, Perceptron algorithm makes few mistakes. Instead of exponentially, you will go to polynomial and n to the fourth or something. I don't know I don't remember by head. And how will you do it? You need to guarantee that in this feature space, you don't know the feature space, but you will assume that in this features, imagine that you assume in this feature space, there is a vector v of small norm. So imagine that you have a vector v in the feature space that looks like this, and that, let's say, correctly classifies everything. Like in the homework, you will get everything correct. This will be 0. So here is the bound we've already proven for the agnostic setting, but also applies to the realizable setting because this thing is 0. That's the bound we see, and we assume that there was a v. But now we're using kernel, so we need to think about the feature space. If we have a good bound here, then we get this as mystic bound. So how can we get a good bound of such form? You need to find x1 tilde some points in the original space, x tilde, such that the decision rules works very well with some coefficients as. So you need to find coefficients and points so that the corresponding decision rules work well. And what is this decision rule? So when we have a new point x, it will just be the dot product in the feature space. And the dot product in the feature space will be a1 phi of x1 times phi of x plus so on as phi of xs times phi of x. So that will be the decision rule. We don't know what is this feature vector. You're only given a kernel, but it's not a problem because you take all dot products in the decision rule. So that means we can find, it is possible to find coefficients a1, x tilde 1, and so on, so that there are no mistakes here. And if you know this, then we can get a good mistake bound and a good decision rules, because this is x1 x plus as k xs x. So after you found such a good decision rules that make 0 mistakes, then you can compute the mistake bound. You get this as mistake bound. So in your homework task, you should find this coefficients a1. So you have to find x tilde 1, a1, x tilde 2, a2, and so on, such that there are no mistakes. And then from this, you can derive a mistake bound, which is here. R is the length of the feature vectors. And the kernel I will give you will be a variant of RBF kernels. And they are amazing because this is always bounded by 1. So in your exercise, I don't remember, it is 1 or some coefficient appears. I don't know the task and the solution by head. But at least something small will be here. And now we need to compute the norm of this vector v. So here is the vector v, and the norm can just be computed in this way. So I forgot the coefficients. Here are ai and aj. So if the coefficients are small and all kernel values are small, so here we have the kernel value, okay, xi, xj. If all coefficients and kernels are small, are of polynomial size, and we have polynomially many points here, then this becomes polynomial. And so this will happen in the homework exercise. You just have to search a bit for these points and then apply some theorem in the end of the lecture notes. So what is written here is just explained in a theorem. And then the only thing you have to do, I guess you have to, so an expression for this will be in the theorem. And so just the task is find these points so that the decision rule that's written here correctly classifies everything. Okay, so this is the end of the lecture. Hope to see you next week. There were some questions, so I will be here.